Thanks everyone. Welcome to Web Unite 2. We're really glad that in the last session we got some very informative messages from Kimberly Tripp, and we really enjoyed those sessions, and we got some pretty positive feedback about that, as Thermaine said. Now we're gonna focus this webinar 2, Web Unite 2. Our focus would be on evolution of indexes. This is a pretty interesting topic in terms of we will start with the inception of when this indexes started. How did they evolve among the different versions, starting with SQL Server 2000 to the depth of 2016. So that's how we're going to cover the depth and breadth of this indexes. But however, always when we talk about indexes, the time would not be one and a half hour would not be really sufficient. So however, we are covering in the right agenda in the right format. So I would want to introduce myself first. It's been more than 13 plus years with the SQL Server. I started with SQL Server 2000, bits and pieces of 7.0. Been working across different versions, starting with 7.0 ideally I can say to 2014 and ready for 2016. And this KDSSG has been founded way back in 2007 as a user group community, and it's a place where we all dedicate our time for sharing knowledge and of course gaining knowledge too. I love core areas like data platform, PowerShell, and virtualization, and that's where I specialize too, and in the HA and DR options as well. And advanced backup and recovery is always a fascinating area, not just the backups though. Upgradation and migrations and performance tuning, and these are some core areas I would leave you to read about it. Also on the personal front, if I'm not with SQL Server, I love to be with my family and kids, and whichever time is left off, I would love to dedicate with on the gym. So I'm in my focus nowadays has been this as an important key point to reduce weight as well. On that note, we'll move forward with the agenda of today. What are we going to start with? The index history. We'll go back in the time machine and see what happened in the past and what's going to happen in the future, and we're going to move between the times now. We will also talk about traditional table storage, how the heaps work, how the heaps get stored, how heaps store data in them. We would indeed talk about the index storage, how indexes store data in them. About the B trees, we would discuss about the B trees and different types of indexes we have in SQL Server. The two main index types, the clustered and non-clustered. We would also discuss about the positives and negations of index and how indexes have evolved across versions. So this is in short about the agenda for today. So I think we're all ready for the time machine ride. We'll start right away. First, going back to when this indexes started, and it's not a recent past, but it belongs to way back in ancient times with Greeks and Romans implementing something called index. There were lots of literature books in those days and lots of scholar works that they were doing, and a lot of data in those days in the form of books though. And that they always were searching for different ways of arranging data and how they can effectively, when there was huge amount of literature books and reading the content back again for a typical person gets tough. So they thought of different ideas. They thought of with table of contents, which we normally have in a textbook, what we have. And then they thought of different ideas like alphabetization, and then came up with ideas of hierarchies of information, different way, the building data in different hierarchies. And finally, I would say they involved, or rather evolved, to implement something called indexes. So this is the word way back in ancient Greek and Romans where this index started. It's nothing new now. However, on the technical digital world, it's different, but on the way back in the ancient history. So if we can materialize and find out quick points about indexes, yeah, as I said, indexes were used way back in ancient Romans, by ancient Romans, and most early indexes were arranged only if we have some letters. In the earlier days, the indexes, the data was arranged only in the form of first letter. So it never used to consider what is there in the next alphabets. It only used to consider the first letter. Then they thought this is a little restrictive, and it progressed towards from first letter to 2 and 3 letters, indexing data based on 2 letters or based on 3 letters. That they called syllable at that time. And back in 17th and 18th century, way back in 17th and 18th century, the data was started arranging in the all the letters. Let's say a word has 15 characters. If we are arranging with based on characters, all the 15 characters were considered for index. And by the later in 18th century, by end of 18th century, close to, they said as per indexing rule, entire data, all the data should be considered, and then only we can arrange data in order. So that was a rule in 18th century. So if we go back and search when this indexes started, I would say approximately in the late 17th century, or rather we can say 1590, approximately in the year 1590. Now, yes, we have, now where did I collected all this information from? There are some book references which I have mentioned in my slide down here, which can help in identifying the same info. Right, so if that is where our indexes started way long back, now let's get into the technical world. Let's talk about from SQL Server side about indexes. But before we start with SQL Server on indexes, the first thing we have to talk is how is data stored? How is my table really storing data? There are only two ways. A table knows only two things. Table says I will store data in any order I want, or a table says I'll store data in an order. So no order or order. These are the only two things a typical table knows, and it doesn't know anything more than that. So when it says I don't want to store my data in an order, you call it a heap, which is not arranged in order. And if you arrange the data in order, you call it an index. So it's a two text context, that or this. Now, and if you can see the heading of this slide, and you can see some Hobbit there, Hobbit. So I would come back and talk about this Lord of Rings story again. We will be very soon talking about in my demo, next slide we have a demo where I'll talk indeed about what is this Hobbit and how we are going to talk about that. So Hobbit, as of now, as introductory level, a Hobbit is nothing but heap or B tree. So more about it in a while, so we'll talk about it. Yeah, so just to quickly summarize on what we are talking, heap is a table without an index, or some people call it clustered index in reality. Index would ideally order the data in a table. So these are two important words, and these two words will drive our discussion going forward. So first thing I would want to do is, yes, I am starting my session with a demo, first with a demo, and then we will come back to the slides and talk a little more later. So if you guys are fine, I would move my presentation towards a slide which I'm going to talk. If you can see my screen still, can you guys confirm if my slides are looking fine? I mean, if you can see my management studio interface. Great. So thanks, Priyanka, helping a lot today. This feedback instant helps you a lot. So I think we would start with our scripts. So I have indeed a couple of scripts which we can open up. And all this content which I'm using today, I'll be immediately sharing after our immediately after the session. We'll be sharing it on the website, so we can get it downloaded from there. Okay, so with that note, I'm going to start this presentation slide. Presentation on the demo. If you feel the font is not appropriate, I'm realigning it. Okay, so this is the first demo which we are talking about, where I would use, where I would create one database called KDSSG index test. This database would help us in all the demos which we are going to use today. Yeah, so I'm creating the database called KDSSG index test, and now we're going to do a very simple thing. We're going to create one table, a table which has only two columns in it, employee number column and employee name column, just two tables, just two columns in it. and I'm going to insert some records into that, where I would say it has index 1 to index 11 and different records in it. I hope you can see them. So my this table name would be called as heap table, because we are not creating any index on this heap table. So it's just a heap. Right. So I've inserted 5 records into this table now. And this command, as we all know, normally we use this command for our database validation, but this time we are going to use it for our table validation. So what does this information give us? This tells that our table name is a heap table and we have 5 rows in it. And we have got to store this 5 rows, this data, all the 5 rows are stored in, I'll zoom it for better appearance. This 5 rows are stored in one page, data page. Okay, and now this is a surprising point to see. There is no index on this table, but we can still see that there is a index size of 8 KB given to us. Now what is that? We will talk in a while. I'll be discussing in detail about this. And so that means our table called heap table has got 5 rows, and it has got 16 KB of space given for it, of which data is one page, meaning all our 5 records are getting stored in one page. And what is this index? We will talk in a while, just now. Okay, so now if you ask what is this? This is a table which got created, and this is in fact a hobbit. I'll fire this command. There's the next one which I wanted to show now. This command, or rather this total query, will give us information, a little more information about this specific table called heap table. Now what information is that giving? We can see it tells that there's a table heap table, and this is the object ID of this table 245575913. Index ID is 0, and this is a standard blind rule we have, that if index ID is 0, that means this table is a heap, and our partition number is 1. In fact, this table is not partitioned. We don't have partitioning for this table, and this is what I was talking about. HOBT underscore ID, meaning either this table is either a heap, either this is following a heap or a B tree structure, one of them. And every table would have an HOBT ID. And if you're observing it correctly, if we can match it, because there is only one partition, this table is not broken into pieces, just a same table. So we can see that partition ID and HOBT ID are same. So when I say HOBT, now I refer one more time, we call it hobbit, and hobbit means heap or B tree, and our table, every table in fact, will have a HOBT ID dedicated for it. And yes, as we discussed just now in the previous command, sp underscore space used, we can see that there are 5 rows in it, and there is no compression implemented here. So this is all about the specific data. So now just to clarify one more time, we used sp underscore space used command, which told that there are one data page and one index page given for it. Now we may have a question saying that why did we get an index page? That answer I'll be giving shortly. If you fire a command called sp underscore help index, it will tell that this table does not have any indexes on it because it's a heap. And now this query, in fact this query is pulling every data from sys.partitions. Sys.partitions is a very helpful internal view which will give us information about hobbit and all this extra information what we need, the object ID and everything. Okay, so that being said, now let us move to the next one more internal sys.system underscore internal underscore allocations. So this is something important here, because by running this command we will come to know our table called heap table. This table is a heap table now. This table has what type of pages? How many pages? Now as I told you already, this table has got 2 pages. Total pages are 2, and we are using of that 2 pages, and in reality 1 page is a data page. So we have only 1 data page. That means this table has 2 pages, one of that is data page. Then what is the second page? We have 1 more page. So we will talk about that, what is that 1 more page, in the next command which I'm going to fire. So and as we can see, this table is stored in a allocation unit called in-row data. Now this is a separate topic overall. When we can talk a lot about allocation units. Now we are talking about something called in-row data, meaning we have two columns, employee number and employee name in our table, and whatever data we are inserting in it is fitting within the row capacity. Normal size, the maximum size of a row is 8060 bytes. The maximum capacity, the row, I mean, if we have a row cannot cross more than 8060 bytes. That is the capacity of a page. A page can have a capacity of 8060 bytes. Indirectly, that means that a row also, if we have one row, a row also has a capacity of 8060 bytes. So that's why we have only one row. We have 5 rows we have inserted, and all 5 rows are fitting within the row. Nothing is going beyond the row limit. Okay, so now we can also see that we have something called first page, root page, first IAM page. Now this information is what I am trying to focus next. If we can see, so I think I'll ideally stop this first part of the demo. This is our first demo, which is where we are creating a simple table called indexed. I mean, we are creating a table called database called KDSSG index test. We created a simple table called heap table, and this heap table has all the information what we need. And we can see also additional information like we have 2 pages for this, and we are occupying 2 pages. So that being said, I'll move to the next demo. But before we go for the demo, I also told 2 words here, which is nothing but HOBT. That means every table has a heap or B tree structure. Either it is stored in heap or it is stored in a tree. That means an index. So that's a quick summary of my first demo of this today. And I would move to the next, back to the slide now. In the slide, this is where we stopped last. Yeah, so this is the same thing which we're going to talk in the next demo. If you can see, if you are, the first content I'm going to talk about is heap. Our focus for the next 10-15 minutes is going to be heap again. How data is stored inside a heap. And whenever I say data is stored inside a heap, that means index ID equal to 0. That means it's a heap. And yeah, so we can obviously can see here that ID, index ID equal to 0 means a heap. And whenever you access data, data is always present in your pages. And in this case, in the screen which you are seeing now, there are 3 pages. And for all the 3 pages, we have one IAM page. Now what does IAM mean? Index allocation map. What does IAM mean? It's one type of a page in SQL Server, metadata page. If you have a table called index test or any table of your choice, or any table which you have, all tables information is present in IAM, meaning how many pages is a table occupying. A table may occupy 1 page or 10 pages. And how many pages table is spreading. Let's say a table has 10 records now. All the 10 records are fitting within 1 page. Then we have it here. If a table has more than 10 pages, then it will start allocating more pages. It keeps increasing its page count. Every time a page increases its page count, table increases its page count, our IAM gets updated. So IAM has a complete clarity of how many pages your table is using. Now, this can be shown here, as you can see. In our example now, I'm going to take one more example which we will talk and see that we will run a command called dbcc-ind, where you can see in my slide itself, which I'll be showing at the demo now, where we can clearly see the page number of IAM. So I'm going to take you back to one more demo. But before we go for the demo, 2 points to observe. A heap, this is the storage format of a heap. Every heap has an IAM page. It's compulsory. Every heap should have an IAM page. Now, data is present in our data rows. An IAM page knows how many pages are there, how many pages your table is occupying. So, hence, our table which we created now called heap table has 2 pages. One page for storing data and one IAM page. So, there are 2 pages for this table. And also, just to clarify, let's get back to the demo. So this is just to show, before we go to the demo again, I just want to show this. See, when we inserted data now, we have inserted in our example, what we have now, we have inserted 5 records. Employee number 1, 200, 500, 59, 11. So these are the 5 records which we inserted. All the 5 records are present in our data page, and information about this data page is present in our IAM page. Assume that we inserted 5 more records, and those 5 more records are on one more page, 154 page, for example. So IAM will know that how many ever pages are there. IAM knows the complete information about all those pages. Okay, so if that point is clear, the same thing which I talked now, I would want to show on a demo part. So if you're fine, we'll just get back to demo one more time. This is my first demo, which simply clarifies. We created one table, we ran some sp_help index, we observed. I'm back to the point. So please see now. We can see that in our discussion which we did just now, if we run sp_space used on our heap table, you can observe that there are 2 pages allocated. One is the data page, which contains all your rows. One more 8 KB, which is nothing but your IAM page. So I'm going to show demo of that now. So as we can see, there are total pages are 2. This table is occupying 2 pages, and of the 2 pages, 1 page is a data page, one is a IAM page. If this has to give clarity, then I think we should run our second demo. So I'm moving on to the second demo of my right now. I would move across to the demo file. This demo file is pretty interesting, and we would spend definitely some decent amount of time to talk about DBCC page and few more commands which are interesting. Okay, so this is our database, and I'm going to fire one command called dbcc page ind. So dbcc ind is another command which will give us clarity about this is our database name, this is our table name, and this table is occupying how many pages. We can see that information. So you can see in both cases, table name is, the object ID is same, and both are in row. The only thing which we have to observe is page type. Page type 10 means that it is a IAM page, and page type 1 means that it is a data page. Yeah, in the next discussion we will talk about page type 2 as well. So if we are observing here, file ID, page FID is nothing but file ID, that is nothing but our MDF file. If you have 2 or 3 files more additional, it can be 3, 4, 5, because 2 is going to be your log file anyways. Page PID. So these are the 2 pages which are there. So 273 page and 272 page, 2 pages which are there in this table. And if we can observe, I already clarified just now, IAM page ID. IAM page ID is nothing but where is your IAM page located. IAM is the first page. So 273 is our IAM, and 272 is our data page. So 272 knows about is 272 information is present in 273. That means page ID, page type 1, data page information is present in IAM page. I want to prove my point. I want to clarify. I just want you to remember that there are 2 page numbers, 273 and 272. Now it's time to move and read about. Yeah, I mean, before we proceed further again, can you see this? There is something called index level. First of all, we don't have any indexes. And all the next page, previous page, all of them are 0. That means no page is connected to another page. In a typical heap structure, one page does not know about the other page, and one page may be located next to each other, or the pages are located completely in different locations or in different files. It is possible. Pages are completely away from each other, not close to each other. They are very far away, but only one page knows about everyone. That is IAM. IAM page knows entire information about how many pages are there. Okay, that proof I want to give that. So let us run a command called dbcc page, and here I'm going to mention our data page. So again, if we are not able to recollect what are the page numbers, so 273 is our page type 10. That means it's IAM page. 272 is our data page. So now here I'm going to give something called 272. So this is a dbcc page command. If someone is not aware or have not used this dbcc page command, I just have one recommendation. It's an undocumented command. So please be careful when you use it in your environments. There's nothing wrong. You can always run this command and see what's inside. but always there's a warning that with undocumented commands, be a little careful. So this dbcc page command means I'm going to run this command on 272. So 272 is nothing but our data page. If you run this command, normally if you don't run dbcc trace on 3604, you can't see the output. So make sure you enable the trace flag 3604. Okay, we ran this 272. Something pretty interesting. When you look at a page, the page structure is broken into, when you dump a page, in fact we are dumping a page. The way the page is stored in your hard disk, we are dumping it and we are seeing it. Now the first part of a page is always buffer. What do you mean by a buffer? A buffer is nothing but this is the information that will be loaded into your memory. So this is how a page, this is the address of the page where it is located, and the hash of this page is 0 for now, but that this information is exactly what is loaded into your memory. So the first section called buffer is about your memory. When a page is loaded into memory, this information is helpful. The next one is page header. Every page will definitely have a page header. Okay, and if you can see M level 0, M level means it is 0. I'll talk more about M level in my next demo. And we can see that there is a slot count called 5. Slot count 5 means there are 5 rows in this specific table. And we can also see our object ID 245575913, which talks about our heap table, and slot count is 5. We have 5 records. This is a free count, how much space left in our page, and the minimum length of the data which you have inserted. So these all things will help us in understanding something about our heap table. And if you can see, I'm paging out 272. I'm dumping 272 page information. So that's what you're seeing now. Page ID is 272. Okay, let's move further. The very important point to see is slots. There are slots in every page. One slot represents one row. If you have 5 rows, you should be having 5 slots. However, in our case, we have 5 records inserted. So it starts with a slot 0. And if you keep scrolling to the end of the page, you will see slot 4. That means we have 4 slots, because every slot starts with a 0 count. So 0 to 4 is 5 records. So in our page now, we have 5 records. This is the dump of a data page. Okay, and if we proceed further, we can also see our data. Employee number 1, employee name equal to index 1. And if you can observe here, it's occupying 4 bytes. That means it's an integer. Integer always occupies 4 bytes. And we are using varchar column. Second column is a varchar column. And because we have inserted 6 characters here, it's occupying 6 bytes. So overall, this record is a size of 4 plus 6, 10 bytes. So it's occupying 10 byte storage. Your total capacity of your page is 8060. Out of that, 10 bytes is used by your record, one record. Okay, and before, I would put all these things little together for you to be very easy and to understand. So I am talking about slot 0 first. So slot 0 says, yeah, so this is our slot 0. This is a complete information about our slot 0. If you can see, there is a record type called primary record. Primary record is nothing but our data. So primary record actually means that we are storing data out there. If this is what I would want to represent as. Primary will tell you information about your records. Primary record. I have written all the comments here, which will help you when you're reading this content later for your reference. These things will really help. For all normal data, whenever you store data records, we call them primary record. So in our case now, you can see that it's a primary record, meaning it's a normal record. And you can see that null underscore bitmap. This is a big discussion which we can't do in this specific time slot given. Null bitmaps are which can be discussed in detail, maybe depending on the next webinars. Variable column. Yes, we are using 2 variable columns here. One column is employee name, which is a variable length column, and employee number is a fixed length column. We have 4 bytes fixed, and variable length is employee name, because varchar always may change. So that is around 6 bytes. That being said, we can also see a memory dump which is done by your record. So this is internally about slot 0. This is our slot 0. Next I'm going to talk about slot 1. So there's nothing to talk. This is going to be literal replication of our slot 1, slot 0. So like that we have all the data. Now just we have to move on to the next point. We saw data page, and I also clarified in discussion that a heap contains index page also, which is not in reality an index page, but it is a IAM page. Now if you're interested to see what's inside an IAM page, I want to show you one thing. Our IAM page number is 273. So what I'll do is I'll do the dump of 273 page. I'll do a dump of it. We can observe IAM page 273. I'm running this command now, and yeah, so as we observed for the DBCC page command, now we'll observe for DBCC page command for a IAM page. This is not a data page. If you scroll down, this will finish off in less than a minute. You don't have much data here because IAM page never contains any data. IAM page knows that only one thing, that there is something called slot 0. Meaning it knows that this table, I mean, again, if you can scroll up and start from the beginning, this is talking about 245575913, meaning our table. And it is telling, this IAM page is telling that this table has only one thing. This table has 272 page. This table is occupying only 272 page. There's only one page. Let's say this table was occupying one more page. Let's say, for example, 275. So it will tell like this. Slot 0 is 272 and slot 1 is 275. Let's say it's occupying one more page. It will say 276, so and so forth. Meaning IAM page contains information about all your pages. How many pages is your table occupying? So IAM is a metadata page. And this is the way you can see the data. And it clearly tells that IAM page is referring to 272. So whenever we do a select command, I'm going back to my PowerPoint presentation. Whenever somebody does a select command on a heap, whenever you do select on a heap, what happens is first the data, when you access the data, when you want some data, first it would touch base the IAM page. IAM page will tell that data is present in data page. Then you enter the data page. Then you start searching every row. Let's say you want 59. So you start searching employee number 1, 200, 500, 59. Even you find 59, you will still continue searching data, because whenever you do a select from a heap, you have to search all the records. It's going to do a full table scan. Okay, just to give a benefit of this discussion, this is how a record is stored. Now, we also should know how records are stored internally in a table. This is a structure of a record, and that's what I was trying to show you now. Every record in SQL Server will have something called, I mean, all the records in page are stored in the form of slots. I think that was demoed and shown. One slot means one record, and all slots start with slot 0 and end with number of records. So whenever you look at the slot portion, so this is how it looks. When you store a record in a page, whenever records are stored in a page, you always have tag bytes first. Then you have null bitmap offset. So these are some metadata specifics which we are not deep diving right now. And you always store fixed length columns. That means an integer, a fixed length column first. So if you have integer and varchar, remember always integer gets stored first, varchar gets stored next. Or and then you have one more null bitmap offset, and then you have your varchar data. So varchar data is nothing but your, let's say you have a char of 100. Char of 100 is a fixed length. So it would store data here. It would not store in your varchar section. So fixed length columns are stored in your in the initial in the row. The first you will always store fixed length columns, and variable length columns are stored next. To prove that point, what I have done is in this demo, I'm going to show the same demo one more time. But when I show the demo, in this case, first employee number 1 is when we create the table. I'm sorry. When we create the table, you created employee number first, employee number 1 first, and then you created employee name second. So employee number is first column, employee name is second column. You can see that it is storing data your employee number data in 0x4. That's the address actually. That's offset where you are storing your data, and it is storing your employee name in 0xf. So 4 comes first in hexadecimal format. 4 comes first and F comes next. So it is storing in that way. If you check, if I reverse the columns, I create employee name first and employee number next. Even then, in that case, it will store employee number at 4th location and employee name at F location. That means it is storing number first. So this is just to prove that always your fixed length columns are stored first and then your variable length columns are stored next. Just this is how it looks. So always I picked it up from one of the SQL website, a blog, which is very nice reference by Phil Factor and few other author. So I can clearly mention that it is 1 byte. Whenever you store a record in a table internally inside a page, first 1 byte is given for status bits, also called as tag bits. Next 1 byte is given for your status bits B, and then you store your fixed length column, and you have null bitmaps, and then you store your variable length column. So this is just to prove that fixed length column and variable length columns, fixed is stored first, variables are stored next. Okay, that being said, I'll take you back to the demo where the same thing I'm going to quickly prove. I'm going to create one more table called heap table 1, insert some records as we discussed just now, and I'm going to do a dbcc page command, ind command, which will tell that we have one IAM page and one data page. Our data page number is 274 and our IAM page number is 275. So I will run this command and show you something here. So as I said just now, integer is stored first and you're in the row slot 0. If you can see, integer column is stored in 0x4 location and this is stored in 0xf location. That itself proves that integer is stored first. Okay, so with this note, this is all I have to talk about our so-called heap. So heap only knows 2 things: IAM, data page, and then your data. And now IAM page may know about 1 data page or 10 data pages. It depends on how many records you have. Let's say my table has 1 lakh records. That means 1 lakh records may be stored in 200 pages. So IAM page knows about all the 200 pages. An IAM page, if you open and see, you know how to see a page now, dbcc page command, but make sure trace on 3604. And you can see internally how many data pages are there for the table, and that's all is there in your IAM page. So this is in short about the total heap structure, and this is all I have about heap structure. Now we will move our focus towards index. Yeah. So heap, as said, there's nothing great to talk about heap. Heap blindly stores data in the pages and tells IAM that these are all the pages, and that's it. There ends story about heap. But index is something little different. Index, as we talked about evolution of indexes from many years now, index is nothing but a tree. Data is arranged in the form of a tree. But to be noted, oops, I think I need to invert this tree. We can't, because normally for a tree, the leaves are on the top, the branches or the intermediate nodes are in the middle, and the root is at the bottom or the end. Whereas our technical index tree is inverted. It's reverse. So you have root on the top, intermediate nodes in the middle, and leaf nodes at the bottom. Okay, and we all should know one point, that we all have been reading at multiple places and so on and so forth, the references that tables, there's a structure, this inverted tree structure, what we are talking about, is called as a B tree. Correct. This inverted tree structure is called as a B tree. We call this a B tree structure. But we should also know that SQL Server does not store data in a B tree structure. SQL Server stores data in a B plus tree structure. So it's not B tree, it's B plus tree. Now, the moment we call as, now there are 2 things, B tree and B plus tree. We should know the difference between B tree structure and a B plus tree structure. Yeah, I mean, there's a joke as well. Some people call it B minus tree. No, it's not B minus tree. It's B tree and B plus tree, B plus tree and B tree. What is the difference between these two things? B tree, as you can see, always there is a restriction. Data should always be present at the leaf node. Yeah, there is an exception here. I'm talking about clustered index now. There's an exception here because in non-clustered index, we're going to talk next about it. Non-clustered index data is not present at the leaf node. The leaf node maps to the actual data, which is a heap. So we will refer to that in the next slide. But here, a B plus tree means that data is always stored at the leaf nodes. Whereas a B tree says that, hey, my choice, I will store data either in the leaf node or I may store my data in the intermediate nodes. See, if you can go back and look at this last slide, normally data is present at the leaf nodes. Ideally, it should be present at the leaf nodes. But for a B tree, there is a provision that it can store data in the intermediate node also. It can store it in intermediate node or it can store it in leaf node, wherever it wants. It's possible. But no, SQL Server strictly says that I will store data, sorry, not SQL Server, B plus tree says that I will store data only in my leaf node or below the leaf node. I will never store my data in the intermediate nodes. And that's not what B tree says. B tree says I can store data in the leaf node or intermediate node. So what is the advantage if we store data in the leaf node at the end of the structure? What is the advantage? It provides lesser height. It reduces the height of the tree and lower heights, and we can search data fast. The height increases, the more you have to search. The height decreases, the faster you can search your data. And now we also improve the cache hit ratio. Now, what do you mean by a cache hit ratio? Intermediate pages are also kept in RAM buffer pool. If you reduce data from intermediate pages, buffer pool utilization can be increased and buffer pool can be utilized well. That's one more advantage we have if we use B plus trees. So finally, if you say compare B plus tree and B tree, the clear winner, and by the way, B plus tree implements something called double linked list, which I'll be showing in the next demo. So finally, B plus tree wins over B tree, and hence SQL Server is using B plus tree. So there are cases where you may read blogs and references that it is B tree, but SQL Server internally uses B plus tree to store all its data. If you talk about index, if there's an index, SQL Server internally is using a B plus tree. Okay, this is how a typical B plus tree looks like in our index terminology. And what I'm going to refer now is a clustered index. I'm not talking about any other indexing type now. The first type of index I want to talk about is clustered index. So if you can see, clustered index data is split in this way. In the heap, if you observe, heap has IAM page and data pages directly. But now, no. You have a root page where you have information about your data, like where is data present. And then you have intermediate nodes, which will help you in going into the data directly. And data is finally present at the leaf node. Maybe this way, if we talk, it would not be clear, but still, one very important thing we need to observe in this slide is every page is connected with the next page. It's a bidirectional arrow mark. So if we can observe here, this page is talking to the next page. You can see connection to the next page and connection back to this page. And these are also connected to the next page and connection back, meaning every page knows about next page, and it also knows, and this page knows about its previous page. They are doubly linked lists. They are connected with each other. That's at the intermediate level. And this is also happening at the root level. Every page knows about the next page. And this is not the case in a heap. A heap does not bother where data is getting scattered. Whereas our clustered index is a bit bothered, but it definitely knows that, okay, my 10 records are present in this page. It knows that where are the next records present. So this is the beauty behind a clustered index. A clustered index technically rearranges your data, and all the data is present always at the leaf node because you are following a B plus tree structure. And these are all algorithms in C language, which we are using in SQL Server. So B plus tree structure, it has double linked list. Now I'm going to show a demo next. In that demo, I'll be talking about records like this. What I'm doing is I'm inserting just 9 records, just 9 records. And these 9 records, like you have IAM page is compulsory, whether whatever structure you are using, whether you're using a heap, that is a heap table without any index, or you're using a clustered index, you always have a IAM page. IAM page is the beginning, the first page. IAM knows about index page, and index page knows about all your data pages. And when you are searching, let's say I'm searching for record 5, I'll ask IAM. IAM will tell that, hey, if you want to know where 5 is, go and ask index page. Now you'll go and ask index page like where is 5? It tells, hey, 5 is present in page 160 because there is an index. There are keys here. There are index keys here. I'll be showing demo of the index key now. And you reach 5 and access your data. And when you're accessing 5, you just access 5. You don't touch any other data. So only in 2 searches you reached your data. However, there are some conditions that index is not very good if you have small tables. If you have 1,000 records and below, index is not a good practice if you have 1,000 records and below. Okay, and that being said, we will move on to the demo of our next quick thing, that is clustered index. Okay, so I'm going to talk about clustered index demo now. It's a very important that we need to understand how our clustered indexes look. This clustered index, we will do the same practicals now. This is my third demo, which would talk a lot about how clustered index store their data internally, and what is really big deal about a heap and a clustered index. We're going to see that now. Okay, so I'm going to move on to my third demo of the day. Okay, I will drop the table which we already have. I'm going to create this table called index table. Previously we had heap table. Now I'm going to I changed the table name to index table. And if you can observe, we are inserting only 9 records. 9 records. And all these 9 records are replicating a character 1,000 times. That means in this example, if you can see here, my data will be 1, 1, 1, 1, 1, 1, 1, so and so forth 1,000 times. Then I'll have 2, 2, 2, 2, 2, 2, 2, 1,000 times. 3, 3, 3, 3, 3,000 times. So if you replicate this, if you repeat this, there's only one observation we all should have. That is, it tells that every varchar occupies 1 byte. That means this is your integer. So integer is occupying 4 bytes plus 1,000 bytes, 1,000 characters. So meaning one record of size in our case is 1,004 bytes. Okay, total capacity of our page is 8060 bytes. So that means we can't insert more than 7 records in this table. In this page, I mean, we can't insert more than 7 records because if you do a math, 1004 into 7 will be 7028. If I insert 8 records, 1004 into 8 would make it 8032. It would still not fit. The reason I'll just show in a while. So we to give a proper demo, I would leave the mathematics and go back to the presentation. I'll show you now. So these are 8 records I'm inserting now. In fact, 9 records. I inserted 9 records into the table. And then we're going to create one clustered index. A clustered index on employee number column. We are arranging employee number column in a proper order. So we are setting only one column in our example now. Create clustered index name on table name in bracket column name. Okay, and I'm going to fire a couple of queries which are very interesting, which will give us some metadata information about our table. Okay, if you can see now, I created a simple clustered index, and when you created the clustered index, we can see that there is a index ID 1. Index ID 1 represents that this is a clustered index. Index depth is 2, meaning the depth of the index. The levels, how many we have is 1. The 2 levels we have, 0 level and 1 level. That means depth of the index is how many levels you have. So 2 levels we have, depth is 2. 0th level and first level. If you can read here, I gave a little helpful documentation. Index level 0 represents it is a leaf node. So if you can see here, index level 0 means it's a leaf node, and the number of records present in your leaf node is 9. Yes, because we inserted 9 records. There are 9 records in your leaf node, and these 9 records are present in how many pages? 2 pages. I just told you that one page can max contain 7 records in this example. It can't contain, so 2 records are present in 2 rows are present in one page, 7 rows are present in one page, so we have 2 pages occupied. So this is about our index level 0. Now next one is index level 1. Index level 1 is our intermediate node. We have one index level which is storing all our index entries, index keys. So if again asked a question, index level 0 is our root, the leaf node which contains all our records, and index level 1 is our intermediate level which contains the information about our index keys. So the same thing which I represented in my graphically. So this is our leaf page. 7 records are present in our page 1, and 2 records are present in page 2. This is one level of the index, which is nothing but leaf level, which is level 0, and level 1 is our index page. If you are searching for 5, it should know, index page should know that 1 to 7 are present on the left hand side and 8 and 9 are present on the right hand side. So that's why you need an index page. So search becomes fast and effective. So this output, this command tells us that how many index levels you have, how many records you have. So these kind of metadata information. Okay, and that being said, I would fire this command called dbccind again. But this time, if you observe, in the previous cases I was always giving a 0, that means it's a heap. Now I'm giving a 1, that means it's a clustered index. See how many pages. Previously you can see that there are only 2 pages. One was IAM page and one was the data page. But now you can see that you have a definite, I mean, whatever you're using, a clustered index or a non-clustered index, always you'll have an IAM page. IAM page is compulsory. You can't skip IAM page. Then we have page type 1, meaning page type 1 is nothing but your data page. So you have 2 pages which are storing your data. And you have page type 2, that means it's your index page. Look at all the page numbers. We need to track all the page numbers. 282 is our IAM page. 281 and 283 are our data pages, and 284 is our index page. So the total 4 pages we have in this specific object, and this object is nothing but our clustered index. This is our clustered index. Let me show you something more at the next level. See, I have put question marks here. Why? Because I want to replace these question marks, because whenever you do your demo, definitely those question marks will be there, and I want you to run this command and replace that question mark with the appropriate page number. So as per your system that generates. Now in my case, in this scenario, it generated a page number. So my IAM page number is 282. So I'm going to type 282 here. And now in the previous heap case, my IAM page knew max about only one data page. But now in this case, my IAM knows about data page, 2 data pages, and 1 index page. I'll be showing that in this command now, dbcc page. So I am dumping the page of 282, which is my IAM page. If you can record and see this information here, I'm dumping 282 page. Please scroll down. Yeah, as we can see now at the end, slot 0 knows about 281. Slot 1 knows about 283. Slot means row. And slot 2 knows about 284. That means as you can see the previous output again, 281 and 283 are data page, 284 is our index page. If I run this command again, I'm sorry about that. If I run this command again one more time, page command, and I am dumping my IAM page. At the end of the IAM page, you can clearly see that your IAM page knows information about your 281 page, which is your data page, knows information about your 283 page, which is your data page. 283 page is containing 2 records, 281 is containing 7 records, and your IAM page contains some metadata. 284 is your IAM page. So this is how, I'm sorry, 284 is your index page. So this is how your IAM page knows about every page which is allocated for a table. Yeah. So now I'm going to run, this is the last one which I dumped is nothing but our IAM page. Now I want to dump this index page, what we have. So to repeat, 284 is our index page. 281 is our data page. 283 is one more data page. So I'm dumping first index page, and you may be very interesting to see this. Normally when you do a DBCC page output, we should be seeing data in this format. Normally when you see with dump data. Now if you don't want to see in a plain message format, you have an option to tell at the last save that with table results. If you do this, it will show output in a tabular form. Great. But whenever you dump at a dash page, a index page, whether you want or not, I'm not putting table results. I'm putting a normal DBCC page command. Output will be always in the message format, but you can see two outputs. One output is about your result, and one is about dumping of the page. So first let's go and see what's inside this page. As always I tell, we have buffer. Buffer is nothing but these are the pages which are loaded into memory. Next is page header. Every page will have a page header. Page header size is 96 bytes. Okay, and then after page header starts your slots. Okay, now we can see here our slots don't have any information. They don't contain any records in them. Slot 0 says nothing is there, you can't see any data there. Slot 1, you can't see any data there. Meaning there are only two slots in this, slot 0 and slot 1. DBCC page command will not dump much information about your slots. If you come back here, yes, here you can see information about your slots, proper slots. Row 0, row 1. What is row 0? Row 0 tells that, again, I'm just doing a bit clarity here. There are two rows, meaning your index structure, the index is broken into two parts, left side and right side. Left side has your data, some amount of data, meaning 7 records are there on the left hand side and 2 records are there on the right hand side. You can see clearly here page ID 281. 284 is your index page. 284 is telling that in page ID 281 you have data up to 8. And up to 8 means 7. So 1 to 7 are present in your 281 page, and this is your first page. And from 8 and 9, records 8 and 9 are present in your 283 page, second page. So this is the key which you created, and this is a clustered index what we created. So, and we created clustered index based on employee number column. If you remember that index creation command which we did just now, it was created based on employee number column. So 0 to 7 records are present in 281 page, and this is what I'm proving technically with the numbers. And now we'll be dumping the page and seeing further. 0 to 7 records are present in 281 page, and 8 and 9 are present in 283 page. And that's it. And you have how many levels? There's only one level. This index is just having 0 level and 1 level. That's it. And that's all I have to share in this about our cluster index. Let's do one thing. Let's dump to prove this, that I told a bold statement that 0 to 7 are present in 281 page and 8 and 9 are present in 283 page. What is the strong proof for my statement? I'm going to dump the page and show you that. See, I'm going to zoom this further for your better view. Yeah, so slot 0 contains what? Let's scroll down. Yeah, you can see employee number 1 and this 1,1,1,1,1,000 times stored here. So that is our slot 0. Then I'll go to the slot 1. So if you keep scrolling, go to the end of this dump page, you can see that yes, there are 7 records present in your first page and there are 2 records present in your second page. I'm doing dump of 283 page also. If you scroll down further, Yeah. So this is 8th record. Slot 0. Slot 0 is 8th record, and slot 9 is, I'm sorry, slot 1 is 9th record. And that's it. This table has only 9 records in it. And did we observe that whenever you create a clustered index, it would drop your original heap structure and again arrange the entire data in physical order. It's arranging the entire data in physical order because there are two pages here, 281 and 283. 281 contains your 7 records and 283 page contains your 8 and 9 records. So this is how data is practically split and data is practically arranged in a proper order. And this is all about your clustered index. So, and whenever you create a clustered index, data is physically rearranged, and this is a strong statement, technically proven. So I would, with that being said, I would come back to my presentation again, and this is all we had to talk about clustered index. So we are now finally talking about one last index called non-clustered index. Non-clustered index is a really helpful index. Yes, we all recommend to create clustered indexes. Clustered indexes are very helpful. Clustered index store the entire data in proper order. Clustered index have their own benefits of them, and we all agree that clustered index is a good practice. Along with clustered indexes, we also have to take help of non-clustered indexes sometimes. So what do we mean by non-clustered index? Non-clustered index is ideally similar structure. Non-clustered index also follows a B plus tree structure, and we have here also root node, intermediate nodes, and leaf nodes. And the only difference is your non-clustered index leaf nodes don't contain data. The leaf nodes will map to your data pages. Meaning a leaf node will tell that, hey, I want record number 5, and record number 5 is present in so and so data page. So the benefit of creating non-clustered indexes is you can create non-clustered index on a heap also. A heap is nothing but which does not have a heap is nothing but which is storing data in whatever order you want, or whatever order you insert the data. And whereas clustered index is following the B plus tree structure. So whether I would always say that non-clustered index is an add-on. You can add extra indexes as per your requirement based on you are using a heap or based on you're using a clustered index. So data is always present in either heap or clustered index, and non-clustered index just contains your keys, just the intermediate keys. Even the leaf node contains the keys. So if we have to prove it, this is how exactly we can prove it. Okay, please see IAM page is again in this example which I'm going to talk now. IAM page we have. IAM page knows information about all our pages. IAM page knows about our index pages also. Index pages knows about our data pages. I mean, if you can see, this diagram almost looks similar to our clustered index, but here there's one more box in the middle called index keys. More index keys. You may have more index keys depending on the column what you're searching for. So let me this also would be very good if we talk on a demo part. So I think we should go to the next demo where I would be showing in detail about non-clustered indexes. We'll take one table, create some non-clustered indexes, and play a little around with that. Okay, so I'm moving on to my fourth demo of today. This is my last demo. And I would recommend when you do your practicals and when you do the same thing, replicate this in your environment. I have given comments for every with explanations, comments with explanations. Probably that may help. And other than this, any questions you have, you can always email me at my mail ID, which is there on this PowerPoint slide, and I'm approachable on the email. So I'm taking it further to the next level now. This is a demo on non-clustered index. And we need to understand, I have split this demo into two pieces and two sub-model. One is we will create one non-clustered index on a heap table, a table which does not contain any clustered index. Data is disordered. On that, we will create one non-clustered index. And one more will create a non-clustered index on a clustered index, both. So first I'm doing demo of this a heap. There's a heap table. I'm dropping the index table one more time. I'm going to recreate this index table. Create it. I'm going to insert some records here. Yeah, so same thing, the same practical what we have done. I'm going to insert some records, and now I'm going to create one non-clustered index. Remember, there is no clustered index created. I'm just creating a non-clustered index, meaning I'm creating a non-clustered index on a heap. When you create this, you'll obviously face an error. You'll get an error because um, the column length. I know if you observe the column length, I have given 1000 bytes. SQL Server has a restriction. You cannot create the key length cannot be more than 900 bytes. I'm not talking about table, I'm talking about index. When you create an index, there is a restriction. Your length of the index key which you're going to create cannot be more than 900 bytes. There's a restriction. So that is why we're getting error and it's saying it can't create. So what I'll do is I may have to drop this table and I will create this time, but I have reduced the size from 1000 to 850, so that 850 plus integer 4 bytes together is going to be 854, and still I am not touching my 900 byte restriction, meaning please understand that when you create an index on columns, it can be multiple columns, it can be some 200 columns also, but if you are combining index, you're creating a 16 column is the limit for our typical index creation, composite index on multiple columns. When you create, we need to ensure that total length of the row does not cross 900 bytes. There's a restriction. So index key size cannot go more than 900. So with that said, I'm going to insert these records now. I've changed everything from 1000 to 850. So our practical goes well. Okay, so yes, I created one non-clustered index. This non-clustered index is created on a heap, and I would fire the same command which we fired earlier. And here, if you observe, it tells clearly that I created a non-clustered index on a heap. For heap, ind ID is 0, and for my non-clustered index, index ID is 2. If I create one more, it's going to be 3. So the more and more you can add indexes. There's a restriction here in SQL Server 2005. Up to SQL Server 2005, we can create max 249 indexes, non-clustered. We can't create more than that. And whereas from SQL Server 2008 onwards, we can create up to 999 indexes. So the index count has increased now. We can create up to 999 indexes. Okay, and as we can see here, record count, we still stick to it. 9 records are there, 2 pages are there. That means 9 records are stored in 2 pages. Maybe 7 records are stored in one place. Sorry, I can't comment saying that 7 records are stored in one page and 2 records are stored in another page looking at this result, but we can definitely comment looking at the next command which we are going to fire. So looking at here, we can't tell that, but yes, there are 9 records stored in 2 pages internally, and one index page is what you have. Okay, so yeah, this command called dbcc ind will give us the clarity now. If you can see, I am not interested in firing this command on a heap because our focus is anyways on non-clustered index. So I'm going to cover the first command dbccind. So what is stored in a non-clustered index? If we are properly seeing this, a non-clustered index has a page ID 282. That means it's IAM page type 10, and 281 is your page type 2. That means page type 2 means your index page. Page type 1 is data page type 2 is index page, and page type 10 is IAM page. So that's it. So this gives us a little idea. Now I'm going to fire dump, and you know the page numbers now. We can see that the page numbers are 282 and 281. So I will replace this question marks with that. The first one is IAM, that is 282, and next one is index page 281. Yeah, please observe this output of this command now. As we can see, buffer first, page header. I'll go to the row slots. So as IAM doesn't know anything, IAM is innocent page which knows only about the pages allocated. So IAM knows about 281. So I'm going to 281 and dump 281 and see. So what's inside 281? See, this is what I call, whenever you query, whenever you do dbcc page command on index pages, you will not get anything in the dump of the page. Please see, you go to the end of the page and scroll, you will not see any data here because these are keys. And technically speaking, this is how your index key looks like. Can you see record type now? Normally record type is primary record. Primary record means data. Index record means your index key. And look at the size of your index key now. 866 bytes. 850 850 is for your the varchar, and 4 for your there are some additional extra metadata things which get added, which is out of scope for this specific presentation now. So you can't understand by looking at this index. This is how a index key looks like. This is how you represent your index key, and we can't see anything properly here. And so that's why you have this fantastic option to watch. Can you see here? We have total 9 rows, 0 to 8 rows, and all these are present. These are index keys. This is how your key looks like. See, if I stretch the whole, I'll run the command again. Yeah. So if we run this command again, you can see that this is your index key, and if you want the whole record, this is the key of your heap. Heap is nothing but your respective, because we created this index, non-clustered index on a heap. So this employee number, if I am searching for 5555, I will search for this, and if I want the complete record, so this is a RID, so row ID. So it will be doing a RID lookup. It will go and search for the row ID and get the row, that complete row. If you're asking for 5, first it will look in the index keys. It knows that 5 is present in 281 page. It will go and search the 281 page, and after it searches the 281 page, it says, oh, this is my row ID. It will go and fetch your row ID directly from the heap and give you that record. So this is how internally searching happens, and this is how your index keys look like. Yeah, and yeah, there is one more out of scope discussion right now. What is a key hash value? So just for the benefit of the time and looking at the content what we have to cover, so it becomes tough to cover key hash value right now. Okay, so this is the demo on our non-clustered index. Now I have done a similar demo where I created one clustered index and non-clustered index, which I'll try to cover quickly. So I'm inserting some 9 records as per se. I'm creating one clustered index first, and then I'm creating one non-clustered index. I did so. Now I'm going to fire this command, and you can clearly see that, and it can clearly see now that we created non-clustered index, and we also have this non-clustered index is created on clustered index, and we have only one page, one index page and one data page getting occupied, and that's it. So this clarifies that whenever you create data in this way, in this format, we can also do the dump and see the same thing. Replace this question marks with the page number and start reading and understand the page. So reading a page always gives more insight, gives more clarity, and you can always not just understanding and reading from books, but you can open the pages and see what's going inside. Right, so I think these are the 4 demos I have for today, and I would want to go back onto the theory mode for some more time before we wrap up and take some questions. So I just have another 5 minutes for, yeah, so I think to quickly summarize, if you have a table, your table is either a heap, your table is either a clustered index, finally when it comes to storing data, or you use a non-clustered index. And if you're using a heap, you always touch your IAM page and then access your data. If you're using a clustered index, of course, IAM page knows about the root page. So you hit the root page. From there, look at the intermediate pages and finally know where is the data located and pull the data out if you're using clustered index. If you're using a non-clustered index, use the root page, check the intermediate pages, check your keys, find the RID or find the clustered index RID lookup or a key lookup, and finally get your data. So this is to summarize what we talked about heap and clustered and non-clustered. Okay, now what are the benefits of indexes? Indexes bring a lot of advantage from select queries side. Indexes gives us clarity on, you can make our select queries run faster. And you know, the most biggest advantage is we can do a range. We can search with a range, and that makes it fast. And data is ordered. Data physically is ordered. That's one great thing and get advantage of using an index. Index improves performance of our hash and merge join operators. Whenever we do a hash and merge joining, so join algorithm is improvised whenever you use indexes. And we can avoid full table scans or index scans ideally by making sure that whatever query you are firing, by covering the query, by making sure that all the columns in the query are covered. That's also called as a covering index. So you can ensure that you can avoid table scans and index scans. You always prefer seeks though. Yeah, and negatives of index. There are so many negatives of index. It occupies a lot of space and agreed that it is also one storage element on the disk. Avoiding nowadays, there isn't a big challenge of disks, so fine. We can. I think this negation is kind of a acceptable negation. Indexes downside on the modification of data. Whenever you do a change in the data, whenever you change a data, first of all, every time you modify data, you have to modify your keys. So this becomes costly. It is a costly affair, and that's how it will be. So this downside is always there with the index. When you modify data, you modify your key, as simple as it sounds. And clustered indexes have a big issue, a big concern called page split. When you insert data in the middle of a page, there are chances of occurring page splits. So more about page splits, as I said, in this one, indexes is a very vast topic and cannot be covered in one specific session. So we'll be talking more on the page splits in the forthcoming webinar. So using too many indexes will cause database slowdown. So please be very careful with creating too many indexes and unused indexes. You create index for one specific situation and you leave it, would cause heavy performance issues. So please drop unused indexes. Do not remove the indexes, or rather disable them when you don't use them. Yeah, and just to summarize and do a one more time review of looking at the past, what happened, present, what are we, and future of indexes. Looking at the past, if you look at SQL Server 2000, we had some great things like indexes on computed columns, meaning these are some advantages, or I can say in other words that this is how indexes have evolved from the oldest version to the most modern version. I'm talking about oldest version. We in SQL Server 2000, we can create indexes in ascending order or descending order. It was a new thing at that moment. You can create indexes, and when you create an index, indirectly you are sorting all the data, you are arranging all the data, you are arranging all the keys and storing data in a physical order. And there's an option in SQL Server 2000 that you can sort all this data in TempDB. Because if you don't sort in TempDB, you will sort that in your local disk. There's a database. If you're using, you can see my practicals now. All my practicals were done on the KDSSG test database, index test database. If I don't say sort in TempDB, all my sorts will happen in my local database, and that would put load on my database. So there's an option, there's a flexibility in SQL Server 2000 where you can sort all the data which you are doing at the time of index creation in TempDB. This improves some great amount of performance. Index creation entirely supports parallel processing. That's another great advantage. You can do scanning and sorting parallelly. You can sort the data, scan the data at the same time. So that again improves performance. And these were enhancements which were done in SQL Server 2000. That means indexes were there even before that. But I'm just picking up from SQL Server 2000 all the enhancements done. And what were the enhancements done in 2005? The biggest advantage is table and index partitioning. You can break your table into pieces, or rather your index also can be broken into pieces. That makes, if you have very big tables in terabytes, you can break them into small chunks, and depending on a range or whatever value you're trying to segregate. XML indexes were new introduction in 2005. Yeah, one great advantage we have in 2005, which was not there in 2000. Whenever you rebuild a clustered index, it will automatically rebuild your non-clustered indexes also, which was resolved in 2000, not resolved, but it was fixed in 2005, where they said rebuilding clustered index does not force non-clustered indexes. It's not a compulsion, right? And we have, excuse me, we have some great things like included columns. Included columns are, which as I said, I'll be covering more about them in the forthcoming webinar, and on index, if all the feedback goes well, and we can talk more about new features and new enhancements of indexes as well in with demos. So included columns you can do in 2005, which avoids this restriction of 900 bytes. We have a restriction, as we saw the demo in a few minutes back, that whenever column range goes beyond 900 bytes, you can't create an index. The replay, that's a solution. The solution for that is included column, which came up in SQL Server 2005. So we'll talk about it. You can disable an index in 2005. You can do an online rebuild of an index with no downtime or a very minimal freeze period for 2005. And 2008, there was a great enhancement called spatial index, or the geographical data which can be indexed as well. You can compress the storage inside index and tables. And there's an enhancement called filtered indexes. So filtered index means you can put a condition on when you create an index. So that was one great enhancement in 2008 R2. And 2012 grows on with the column store index. Column store index tells that there's no more point in storing data traditionally, meaning you can store column-wise indexes. You don't store row-wise. You can store them column-wise. So indexes can be implemented on column as well, just on a column. And we have a selective XML index as a new enhancement. X velocity. So I would also want you to read this PowerPoint presentation later when you find time. There is something called X velocity memory optimized column store index, so which was introduced in 2012, and this is more for in-memory as a startup for the in-memory processing. So this was introduced in 2012. And index creation entirely supports parallel processing as said so in the previous versions. So, and 2014 brings up some more things for us. 2012 we had column store index, and 2014 we have clustered column store index, where you can update your column store indexes, and you can do online index. There is a normally when you do an online index rebuild operation, you can't tell the exact tracking, how much time is complete, how much time you want to know. If you want to monitor properly, if you want to monitor your online rebuild process, how much time it is complete, there's a feature in SQL Server 2014. There is an event class added called online index operation event, through which you can monitor and tell how much index rebuild has completed. You can get some more clarity on how much time more it will take. See, at times we face this issue in Office that we are doing a rebuild operation and you don't have an answer for your customer, or your application folks asking how much time will it take. 2014, you have an answer for it. You can tell that. So yeah, in 2014 also you can rebuild only one partition. Earlier we had to rebuild the entire partitions, all partitions together. In 2014 you can only rebuild one partition. Yeah, and yes, this is what we are all waiting for. And I think with this I would stop my presentation, because I'm end of my presentation now, and which also gives us some reference links you can go through. And thank you for attending this Web Unite of Web Unite 2 for indexes. And if you feel that the session is informative and we should continue with more sessions, we would encourage to be with or like us on the Facebook and also the Facebook page what we have.